Caitlin, Kira. All right. Look. I'm ready to go. All right. Any burning questions before we get started? Really need to figure something out before you move on or whatever, anything like that? It's an unrelated, well, it's a next topic. It's not more of the same right now. So if you're super confused with simple harmonic motion or something, it won't affect this lesson anyways. All right. So we are finally actually learning about momentum. So we can make sense of what you've heard to do with momentum, or what from now on, maybe when you're hearing momentum used wrong, you'll hopefully cringe the same way I cringe when I hear it, because it's like the most misused word in physics, it seems. So question is, okay, if we're talking about momentum, just to get you thinking about momentum, if an object's flying at your head, I said something's flying at your head, look out. What two questions would you need to ask in order to sort of figure out the level of danger you're in? What would you think? What you need to ask if something's flying towards your head?
How fast it's going?
How fast it's going is one for sure. Yep. And what else? What if I said it's going pretty fast? It could be going like, 50 kilometers an hour.
Like how heavy it is?
How heavy it is. That's right. So the two main questions. There's nothing really else that matters, right? We ask what the mass is and what the velocity is. Just point out, actually, you said how heavy. That means the force of gravity, which of course we know is tied to the mass. So essentially, I interpreted what you said as and you need to know the mass and the velocity. And what that's doing is it's sort of describing how much it's going to hurt, right? So it's traveling 50 kilometers per hour towards your head, but it only weighs like 0.001 grams. It's like a tiny speck of dust that happens to be blowing in the wind, and it's going to hit your head, and you're not even going to notice it. But if it's a brick, a couple kilograms flying towards your head at a fast speed, it's going to hurt, right? And so what we're doing there is we're basically describing, like, roughly speaking, the quantity of motion, right? Which is kind of funny because I'm not using the word that often gets used so inappropriately, right? That's actually momentum. Okay, so momentum is that quantity of motion, basically the mass and the velocity. So we end up actually just taking those concepts that we know are to do with the quantity of motion, or the however you want to word it, and it's just mass times velocity. So momentum equals mass times velocity. Okay, so P equals momentum. I have this on another page somewhere, but P equals momentum. Since mass was used for, M was used for mass, right? That's why it's a P, I guess, right? M used for mass, so we couldn't use M. M equals mass, of course, and V equals velocity. I know this is typed somewhere in the lesson already, but I'm just feeling I should probably just put it here for now anyways, at least. So if you're looking at the units of momentum, we've got kilograms and we've got meters per second. So quite literally, it's just kilograms, meters per second. That's the units of it. If you looked at, we could say momentum is proportional to mass, and it's proportional to velocity, and basically end up with more mass or more velocity, end up with more momentum, right? But anyways. The proportionality constant was just chosen as a 1, basically, right? You just say, oh, if there's just a product of the numbers, that's the momentum value. There's no reason to have any other proportionality constant in there. So that is momentum. Any questions so far about momentum? We're going to do a lot with it, but for now, you get the basic idea of it. It gives you an idea of the quantity of motion.
Mr. Horn.
Yeah, go ahead.
Sorry, what was the thing that you said it's commonly mistaken for?
So momentum often gets used somewhere in this slide along here. Probably this one down here. Yeah, the way momentum is used in common language, like a hockey team has momentum because they've been winning lately, or in a pseudo explanation, they'll be like, oh, well, when something has, like they end up, whenever someone uses the word momentum and stuff or sort of or kind of, in a description, it's because they're not really explaining things fully. They're just giving like a rough explanation with a lot of details left out, and they throw in the word momentum and stuff and so on in there to make it sound good. Is that what you're asking?
Yeah, thank you.
So momentum's often used very loosely and very wrong. And you've heard me say that multiple times on videos. I can't think of the exact videos, but someone will be describing something and they'll be like, oh, well, because the momentum increases or something. And in that context, in the recent video, I remember saying, well, really, they could have just said the velocity increases. They don't have to talk about momentum. That's a more complicated concept that's necessary in some cases, but wasn't in that case. But a lot of times it's just used flat out wrong. Example could I use? I don't know. I'm not sure. If I come across another one, for sure, it'll be obvious, right? When we see it, it'll be like, oh, they're not really talking about momentum there. So momentum is what it is, right? An important thing about momentum is, and this is guaranteed always, okay? Momentum is always conserved, okay? If you're talking about a complete system. So momentum, total momentum, another way of saying momentum is conserved is that the total momentum of a system is always, the change, sorry, in the total momentum of a system is 0. So there's some questions in the homework about the idea of a total system versus just an object. Like if you think of you pushing on throwing a ball, let's say, if you're considering you and the ball, then the momentum before and after you throwing it is the same. And what you're going to see soon is basically if you were on, say, a slippery pond and you threw a heavy ball, you'd end up going backwards, the ball would go forwards, right? So you'd have no momentum at the start. And then you'd have like a negative momentum and a positive momentum that would cancel out in the end. And so there'd be no momentum at the beginning and the end, right? The trick that makes this seem not true is obviously you could throw a ball and you don't end up with any velocity backwards, but then the system includes Earth in that scenario. Friction attached to the Earth are able to stay still, able to stay stationary when you throw a heavy ball. You don't end up with a backwards velocity. But if you include all of the momentums in the whole system, then yeah, momentum is definitely conserved if you're looking at all of the forces and all of the interactions. One of the questions in the homework talks about if you have an object, say it's getting attracted by Earth, right? And you have an object, so you have an object that moves towards Earth, and it has like v1 and it has v2, and so of course this velocity is velocity. Oops, the other way around there, but that's too much. So this one is of course greater than, right? You end up with a larger v2. So you have a new velocity, you have more momentum, right? So you have more momentum in this final case. So it certainly looks like the momentum of that object is increasing, right? And it is, of course, increasing. But the trick that we're going to see soon is that for this, if there's a gravity force down, then there's also an equal and opposite reaction force of gravity up, right? Gravity acts on both objects. And so basically you're getting an increase in momentum, like a positive momentum change this way. And then if down is positive, I guess, right? And then this force does, affect Earth, but obviously makes the momentum actually be the same here. But the issue is that the giant mass would make that velocity not noticeable. So I don't want to worry about that too much right now. I'm actually going to delete it from this page, but we are going to mention that again soon, and hopefully it all starts to make sense eventually. Okay. So if you're talking about a whole system, momentum's definitely conserved. But if you're looking at like, oh, well, an object was sped up because of gravity or by a repulsion from a magnet or whatever, you could say, oh, it ends up a new momentum amount. But if you can consider both objects involved, then the momentum total is the same. Anyways, So let's just look at some regular old questions, first level stuff, right? We've got momentum equals mass times velocity. So there's another 3-variable equation. I suppose I could load up the equation sheet. People complain there's a lot of equations in physics or science in general. Any science that is explaining concepts, relationships between things, the relationships inevitably end up being mathematical. So there's an equation to do with it. So if you're learning about how things relate, how quantities relate to one another, which happens a lot in physics and it happens a lot in chemistry as well. Biology tends to be a little bit less that way. It's less a mathematical process, right? It's just more ideas like, oh, you got DNA, and it, like it's concept processes. But anyways, here we go. Somewhere down here, I have momentum added onto our well-organized here sheet. So there's momentum. There's where I remember I said it was written somewhere. I remember typing it. So there it is, right? And it is a vector quantity, and you're going to see that in the examples we're going to do. Okay, so that's added to the list. All right. So here's it in action. Blah, blah, blah. They gave you a mass and a velocity, and they're asking for momentum. So put the numbers into the equation, calculate the momentum. Like, not exactly a challenging level of a question. I hope you recognize, as long as you know the equation to do with it, plug numbers in. Okay, so I don't intend to leave this page very long, but as a basic example, just get the basics of it down there if you want. We're going to do so much more with momentum than just this starting level. So stay tuned. All right. So another important thing or concept to do with momentum is what they refer to as impulse in the lessons, like actually momentum and impulse. Impulse is the word they use for some reason in science. You don't really hear it, but in life as much. But if someone's impulsive, they change their mind a lot, right? And stuff like that. So change in momentum is called impulse. I'm not sure which one came first there, but anyway, so delta P, right? Change in impulse, change in momentum, sorry, is impulse. So, for an individual object, right, you can have, of course, a change in momentum of an individual object like we're talking about. The overall momentum stays constant, but individual momentums can obviously change, right? You can have things pushing on one another. It turns out that, oh, I should supposed to show that last, I guess, but here we go. So let's do this. In order to change momentum, a force has to act, right? So I'm reasoning out this formula that you just saw, okay? When a force acts for a certain amount of time on a mass, it changes its velocity by causing acceleration, right? So it changes, it causes acceleration, which changes its velocity. That's pretty straightforward. So we are developing this result, force times time, okay? So in other words, you get a change in momentum. So you get basically your change in momentum equals your mass times your change in velocity. And then, oh yeah, in calculations, you're like, oh, momentum 2, final momentum minus initial momentum equals m1, mv2 minus mv1 if you're looking at, the regular change idea, right? So that's nothing new. But change in momentum equals mass times change in velocity. Basically, you can take your momentum equation, momentum equals mass times velocity. It's red. And you can just stick a change on each one. Change in momentum corresponds to a change in velocity. Okay. So we know that force equals mass times acceleration, and acceleration is delta v over delta t. So what happens is you notice in that Newton's second law there, you notice that the mass times the change in velocity is really your change in momentum, right? So it's not very hard development, because then you're like, oh, okay, so in other words, force, your net force equals your change momentum divided by time. So you just multiply both sides by delta t, and you end up with that equation. Change of momentum, delta p, call it impulse, equals force times time. Okay. So that's on the equation sheet 2. If you're adding it to the equation sheet as we go, we got delta p equals f delta t. Go back to the main show here, though. Okay, and you can list, obviously, F equals the force applied, and the time is how long you applied the force for, and delta p is your resulting change in momentum. Now, the concept that comes from this that is really important, you'll see major applications of this in the world around you once you understand it, and certainly in the following slides as well. But the big consequence of this concept here is that if you have a small time interval, right, then say you had a change of momentum of like 100, okay? If that happened in only like 2 seconds, then the force must have been 50, right? But if it took like 100 seconds to happen, then you could tell the force would only be 1, right? 1 times 100 would be 100, just like 2 times, or 50 times 2 would be 100, right? So the concept I'm leading to there is that the smaller the time, the larger the force, and vice versa. Okay, and that's a big focus for the next few slides. So, yeah. Anybody need that page longer?
I think it's okay.
Okay. All right. So concept-wise here, right? A big force with a small time, or a small force with a big time, gives you the same change in momentum. And it actually ends up linking to like vehicle safety and all sorts of things. Let's just watch this for starting here. It's not the most exciting video ever, but it's factually correct.
I dropped the hammer on the end of the nail.
Oh, wait, now we gotta start at the beginning. It's because I looked at it recently to make sure it was working. So it's impulse momentum theorem, they're calling it, right? Rather than just calling impulse. So maybe you should have, well, impulse is this, right? Impulse is this thing itself, force times time. But then the impulse momentum theorem is to do with the idea of the size of the forces and the times. Okay, so that's what I want to focus on for a bit here. Make that a little bigger for you. All right. Cue the exciting video. Maybe.
We're going to be looking at some applications of the change in momentum relationship. According to that relationship, impulse is equal to change in momentum. As an example, suppose that I drop this brick to the table. Now, in the collision, the brick underwent a change of momentum. That's its final momentum minus its initial. The final momentum is what it has now when it has come to a stop, so that's 0. The initial momentum is what it had at the instant that it hit the table, and that depends upon how far I dropped it from. Now, if I were to drop the brick,
visualize. So let's be pausing here. There we go.
Change of momentum would be the same.
There we go. Finally paused. Anyways, when he dropped it,
at the instant that
it made a loud noise, right? Somewhere along here. Slam, right? If your fingers were in there, it would hurt, because eventually he's gonna lead to the idea that there's a large force there. Then he's gonna drop it onto this sponge. So think about why the force ends up a lot less on the sponge.
On this cushion.
Or cushion, whatever.
His change of momentum would be the same as it were for the table, because the brick comes to a stop. That's its final momentum, which is 0. And its initial momentum is what it had at the instant it hit. And if I drop from the same height, that's the same as it was for directly on the table.
Oof.
What is different in these two cases is the amount of time that the collision lasts.
I'm just going to pause there so I can emphasize this. He's not maybe emphasizing as much as I might want him to. The difference in these two cases, the brick slamming onto the table versus the brick coming to a soft, gentle landing on the cushion, is the time that it takes for the momentum to change. Okay, so the initial momentum is 100 kilogram meters per second in both cases, right? The final is 0, so they both change by 100, right? But if the collision took, decimal zero, like a very, very small amount of time, like decimal 0.01 of a second, then the force has to be appropriate, has to be big in order to multiply to give you the momentum change. Whereas here, maybe the brick comes in and squishes into the cushion and then rebounds back, and that whole time it's squishing and coming back, that's a longer time interval for the collision, right? And so then a way less force is necessary. So I think
in the case of the cushion, you can see that the cushion depresses. You can see the cushion compress, and that takes more time than if I drop it directly on the table.
Okay, so I think I've already explained it enough. We don't need to keep watching him. He's a little bit slow. But so basically, we know for a given change of momentum, you can have a large force over a small amount of time, or you can have a small force over a long amount of time, or a large amount of time. I should just say large there. It makes more sense to use the same wording. But all right. So we're going to put that to good use in our analysis of situations, right? So that's the impulse momentum theorem. And you can see it graphically here too if you wanted, where you're like, okay, so remember we talked about the area underneath the force times graph is the moment. Well, actually, wait, we talked about it recently for work for gravity, for energy stored and so on. We're using the concept yet again. That's why it seems so familiar, to represent impulse. Okay, so we got area under a force time graph is actually impulse because it's force times time. So it's that area represents the change in momentum, right? So that's your impulse, that's your change in momentum. So this time interval of delta t, that whatever number that would be, and this force combined to give a certain amount of area, a certain amount of impulse, right? If we had a shorter time interval, then we'd have to have, like if I had a shorter time interval, like only say this long here or whatever, my diagram over here is actually going to be half. So picture it being half here, how you'd have to have a higher height, a higher force in order to have the same amount of area, right? So graphically, it's making sense as well here that, we'd have, if we had a shorter time interval, we'd have to have a larger force to get the same area, or in other words, change momentum. If I went to an even shorter time interval, right? If I went to like, tiny little time interval like that, then this area would have to be something, it would have to look like this. If I can steady my hand a little bit here, right? It would have to be something like that, right? Maybe that's the same area. A really big force, right? Large force for small delta t. Each time the areas are the same, change of momentum is the same, just the force needed is different. Questions about that? Okay. Yeah. So a good application of this, the smart car crash test silly clip. And after we watch the video, we're gonna watch the first 50 seconds. Here we go. A little bit more exciting of a video.
Coors Organic is made of organic barley, organic hops, and 90 calories.
Inappropriate.
Coors Organic. It's organic, but chill about it.
The key to its defences is its so-called tritium safety cell, a rigid steel cage reinforced at key points. Smart described it as the hard shell of a nut, with small but efficient crumple zones both at the front and at the rear. In theory, getting inside...
I'm going to pause for a second. Small but efficient crumple zones. Define the word efficient in that context. It's advertising jargon. It's like dishwasher detergent gets your dishes virtually spotless. Virtually spotless means they're going to have spots. Virtually means not real, just like virtual images in grade 10 light, in the grade 10 light unit. Anyways, keeping going.
It's like putting on a suit of armor. Even when it hits something more than twice as heavy, the bit where you sit is remarkably unaffected. There may not be a long crumple zone, but look how the Smart's windscreen remains intact. This is testimony to the rigidity of the passenger cell.
So they are, in advertising, trying to convince you that that's a good thing. I'm pointing out here, is it really a good thing to have that rigid cell? Thoughts? Any thoughts?
No, like without like my instinct would be to say that like the rigid cell wouldn't absorb the impact as well, but I don't really know.
So what's going to happen in our analysis? You're absolutely right, but in our analysis, what we're going to end up talking about is, you know, the change in momentum that this car has versus this one. At one point in this video, the big car was actually still going down the video, down the screen, right? So this big Mercedes or whatever it is still going this way, whereas the smart car actually reverses direction while this one's still going that way. Someone in this car still has momentum forward. Someone in this car now has momentum backwards. This person has a bigger change in momentum. That's not a good thing. Having a rigid, hard shell to quote unquote protect you is nonsense. It just is flat out nonsense. So when we think about this, what is a small but efficient crumple zone? You need space. You need distance in order to have longer collision times, in order to have smaller forces. I'm actually analyzing the fact that what they're saying there is just wrong, based on this equation. Where's my text button here? I just need to grab the delta button. I should just write it, it'll be faster, right? We're based on the idea that the change in momentum equals, it's supposed to be faster, delta P, right, equals F delta T. We need to have a longer time interval by having big crumple zones, right? And or if you put it in terms of force, it ends up being force, as we had on the other page, delta P. Oh boy, force equals change. Well, why is it keep doing that? It did the exact same thing again there. Delta P over delta T. That's so weird. All right. The mysteries of the touch screen. Anyways, so if this number is big, right, then this number overall can be small. If this number is large, then this number overall can be small, right? So there's no such thing as an efficient crumple zone. You just have to have physical space in order to have the collision take longer, resulting in less force, right? I pointed out already that at one point in the video, the large car is still actually moving forward. I said to the right, but still moving forward after the smart cars actually stopped and started moving backwards, right? A person in a larger car would have less momentum change, therefore less forces, therefore less chance of injury. It's just undeniable science, right? So this video, and if you look at commercials for smart cars, they're not going to talk about the reality of it at all. They're just going to continue with their, it's a rigid cell. Look at how tough it is, right? And a lot of people are convinced that's a good thing. This video is actually scientific, and so this lady kicks in here and has some more logical, more true statements to do with this. Listen up.
Outside of the shell's rigidity.
So.
The downside of the shell's rigidity is that there's a greater potential for the crash forces to be transmitted through to the passengers. Ideally, you want to slow them down as gently as possible.
So that rigid cell transfers those forces to you nicely. That's the efficiency of the crumple zone, I suppose. It transfers those forces efficiently to you. She's saying here, ideally, you want to slow the people down inside the car as slowly as possible. You want to slow them down as gradually as possible. You want a longer time interval, because that gives you less force. That's the impulse momentum theorem in action, right?
You get seatbelt tensioners that stop you lurching forward violently, and they're fitted with force limiters that give you a bit of slack before they dig into your chest.
So that is a legitimate safety feature. They have, obviously the seatbelt locks when you need to stop and you need it to hold you in place, right? But instead of it just locking solid, they have it set up where it'll actually give a little bit. Right, so basically, it'll allow you to, move out. I don't know what distance, maybe a half a foot or something like that from the chair, to help you slow down gradually within this vehicle that is not going to be slowing down gradually because of its physical properties of how tough it is and how light it is. Right, honestly, like there's no getting around. Bigger, heavier cars are safer. They just are. it's undeniable physics. But this seatbelt tension limiter, so instead of it going to whatever crazy amount of force you would normally have in this, if it didn't give a little bit, it'll give a little bit, giving more time for that momentum to change, which allows the force to be less. So there's definitely good science in that claim right there.
The car is also fitted with a driver airbag, a passenger airbag, and a steering column that will retract out of the way in a crash.
So the steering wheel retracting out of the way in a crash, that's them acknowledging that you don't want to be impaled on this thing, right? So if you did start to hit it, it gets out of the way and allows you to have more room to slow down. Another legitimate safety feature. They have self-collapsing steering wheels. I don't think many cars have that. So there is some legitimate safety designs in this car. The rigid cell isn't really one of them, right? But yeah, they kind of have to have it if the car is going to be so small and so light. They have these other features worked in to try to help save your life, I guess, right? But yeah. Oh, the other one they talked about was, what did they say? Airbags. We're gonna have a whole slide dedicated to airbags. So I'll talk about that in a second.
That will retract out of the way in a crash to give you more room to slow down.
That's the theory, but no one knows how the car will behave when it's crashed at 70 miles an hour.
So they fit this thing with a remote control.
We've enlisted the help of engineering guru Dr. James Brighton. His team have converted a smart so that the brakes, steering and throttle can be operated via remote control. Dr. Kim Blackman will guide the smart from a chase car straight into 20 tons of concrete block. It'll be similar to losing control at 70 miles an hour and steering off into the temporary barriers on a motorway.
So over 100 kilometers per hour, 70 miles per hour is like 115 or something.
Kim to James, 10 seconds.
And they're going to amp up the suspension here, or the suspense in the video here. Suspension. And eventually, slam! Oh yeah, look at that rigid cell. You're going to be safe. Oh my good lord. You stopped instantly, right?
From 70 miles an hour to naught in 1
Not
second.
meaning zero in British Britain land.
20 tons of concrete leapt into the air and rebounded to the side of the road. We didn't know what we'd find when we reached the wreckage.
So here's him coming along and analyzing things now. Actually deflected the barrier a little bit.
Steel cage has certainly done its job really well.
Oh yeah, the steel cage has done its job well. Stay tuned.
Still see the original shape, just that one nasty kink there. Don't forget this is a car without a roof. The plastic was just shattered. So without even the strength of the roof, there hasn't been that much effect. You can open the door.
And that's on the worst side too. You can open the door. Now, the gruesome reality of this is that it would make the paramedics easier for them to open the door to carry you out of the vehicle, because you wouldn't have survived that, right? Like it's yeah.
So when you come around the front, you do see that massive impact. Around the other side,
so it did crumple a lot, and with those safety features inside, maybe you'd have a little bit of chance. But
like a smart guy, because of the full shape of the door. Indeed, the door not only opens normally, closes again. That does show.
So obviously a very strong structure.
Cage has worked on this impact.
But
So we found out.
to say that a feature to do with a car worked to be a safety feature, you'd have to say it reduced your forces, and that certainly would not have. So, yeah, another example of it, but in some analysis afterwards. So we're watching here. Oh, nerds! I haven't had nerds in a while. Good sugar delivery mechanism. I don't know if I've ever seen an ad for nerds. Yeah, maybe back in the day. All right. Hard
Real-life
text, the
safety.
new smart.
This philosophy applies to all Mercedes-Benz and smart vehicles. The main focus in their car-to-car crash tests is the compatibility of vehicles of different sizes and weights. Smart versus S-Class looks pretty much like David versus Goliath. And they will collide to demonstrate their high safety standards.
So again, right about now, that smart car is actually going the other way, right?
Passenger compartment remains intact.
Right there, the smart car stops, the other car is still going forward. That's not a good thing.
Safety is no matter of size. The forces on the occupants were significantly lower than the biomechanical limits. Test passed.
So supposedly they had force sensors in there and they were less than the, what the safe amounts. But that reducing thing, whatever a tritium safety cell is, to use fancy words, right? But of course keeps the hard shell intact, but that leads to a greater change of momentum, as I've mentioned multiple times, and greater forces, more chance of injury, right? So again, the car actually stops, goes the other way. That's a bad thing. The cell being intact and so on, like I said before already, it just makes it easier for a badly injured person to be removed from the vehicle, which gets you to the hospital quicker, I guess, if you actually survive. So I guess you can put a positive spin on that. So anyways, so the more time you have to crumple, then the more time the collision can happen, right? So this is for a given change of momentum, what force do you need? And so if it's going to be a very short collision, you need lots of force. If it's going to be a long duration collision, then you can have a much smaller force. And it goes along with that area graph that we talked about before. Okay, so like I said, there's going to be a slide dedicated to this. Obvious question: what are those for? What's the main purpose of those? As a physics answer to this, what's the main purpose of those? Anybody?
Like slowing down the time until you like make an impact with something, or
I love it. So slowing that time. In other words, making the time of the amount of time it takes for your momentum to change as long as possible, right? That's exactly the best answer I would want to hear as a starting point for this. Is airbags, they're designed to make your change momentum take longer. So basically, instead of having your body, here's a human not drawn to scale. It's not exactly anatomically correct there, but instead of them moving, if you didn't even have a seatbelt on, right? You're like going ahead with the velocity the car had in a head-on collision, and you're slamming into the steering wheel and the dash and the windshield and all that, right? So your momentum's going to change extremely quickly there, right? Instead, in this case, you come ahead and you hit this airbag, and it would apply a force on you. So now you're changing momentum all the time. You're changing momentum all the way until then you really start to change momentum here. But you've lengthened the time of the collision, and so you've reduced the forces. That's what they're for. That's 100% what they're for. That's all they're for. That's all they do, right? So they increase the length of time during which the collision occurs. This reduces the forces that occur to change the momentum. That's it. That's all. And then they deflate afterwards and need to be need to be fixed and so on. They don't provide any benefit after all. In the end, sorry, after all it's done. So if we had an example showing the idea of working with the new equation, here's a 57-gram tennis ball. Convert that to 0.057 kilograms. It is struck. It's going upwards, right? And then it's struck just as it comes to rest at the top of its motion. All right. So starting out at rest, and you're hitting it. You're hitting it with a force of 420 newtons, or 4.2 times 10 to the 2. So you can clarify that there's two significant digits. And it says determine the speed of the ball after the collision if the average force is exerted for a certain time interval, right? So basically, because you're given a time interval and a force, you're going to be able to calculate the change of momentum. And then since you know the mass, you're going to be able to figure out the speed or the velocity. Okay. So this part here, they're saying that the force times the time equals the change of momentum. They're writing it way more complicated than you need to, but long story short, let's show the more understandable version of things. It's kind of nice for you to see this, though, like I said, because you're gonna might end up looking up, resource materials places, and it gets written in a weird way. But they're talking about the force times the time. So basically, we're saying delta P. I'll write it maybe in the same order at least, but F delta T equals delta P, right? So you're saying, okay, force times time. Our force and our time were, what was it again? 420 newtons and 4.5 times 10 to the -3, right? So we've got the 420, and I'll have to move my equal sign in a second here, but 4.5 times 10 to the -3. Oops, now. So move stuff around a little bit here, make sure I can, wow, lots of different pieces. So I've got this calculation. There we go. That's change of momentum. So we can get a change of momentum value, right? And so that would be the 420 times the 4.5 e to the 3 negative. So 1.89. The momentum changed by 1.89 kilograms meters per second. That's units per momentum. And then after that logical thing that we just did, we can say, oh, and we know that momentum equals mass times velocity. I would even go so far as just to say, well, why don't we just use the delta P equals m delta V version of that? And so we'd have the 1.89. It's going to equal the mass, which we were given as decimal 0.57. And the delta V obviously was calculated. So we do the 1.9, I still have my calculator, divide by decimal 0.57, gives you 33.15789474. So I've been doing this like this in the homework, where I'll say like 33.1578 ... I'm not even actually rounding to a reasonable number there. That should actually be a 9 if I were rounding. I'm indicating I'm keeping numbers. But in the end, of course, you're like, oh, okay, well, I change velocity. I'm going to use the 2 significant digits. So 33 meters per second to 2 significant digits. Supposed to be meters there. Okay, so the change in velocity is 33. They asked specifically for the speed of the ball after the collision. So I suppose the final step would be to point out that final velocity minus initial velocity is your change in velocity, right? So you'd have, need more page. We'd have 33 equals my final velocity minus my initial velocity, which was actually 0. So of course I'm getting my final velocity is 33, right? Now if you wanted to talk about directions, we could call it, they did have newtons, they didn't have any directions here, basically forward, I don't know, right? But I wasn't too worried about directions along the way here, but this would have been forward, in which case it's a vector, and this would have been forward, in which case it's a vector, and all these could be vectors, in which case it's positive, meaning forward. Right? Anyways, yeah. So they probably have a vector answer in here in the end, but they don't even actually. Probably would have anyways. So again, the idea of having to keep a bunch of decimals along the way is what you would do anyways here. And so I almost wonder if this is the main reason they do it so confusing in textbooks. So they don't have to have a 33.1578 ... in the textbook. As a textbook author, if I ever take on a job authoring or making, like authoring a textbook, I wonder if that's going to be one of the things that I'll have to like fight them on. Like, seriously, why not make it so more understandable? And they're going to say, oh, because we don't want to have all these decimals in the book. Anyways, let's see how that might work. Okay, does that make sense? So that's all of those concepts rolled into one there, making it much harder to follow. Step by step, do this, then this, then this. Much easier. Okay. I heard a mic key there. Is there any questions?
Oh, sorry. I was just going to say that was fine, but thanks.
a verbal thumbs up. I appreciate very much. The other part here was what? Repeat the calculation assuming a time interval 5.3. So let's not do that, but instead of 4.5, it's 5.3, right? So now you're operating that. This isn't really the impulse momentum theorem, right? This is you're operating a force for longer, same force for longer. And so you're going to get more change in momentum, you're going to get more velocity, right? But if we're talking about a collision and we said, oh, the collision takes longer, then, so it ends up going 39 instead of 33 there, or whatever, right? If it was a collision situation and the collision took longer, then you'd be able to say, oh, the force is less. And we'll see examples like that soon. So this idea of a follow through here, if you're swinging a racket and you have follow through with your, like in baseball, they say that the batter is a good hitter. They swing through the ball. They keep the bat going even after it hits the ball. So they're putting a good amount of force on it to make that happen. That, of course, increases the amount of time that you're acting, making that force act. Okay. So this isn't really it's maybe not the best example to have right after this impulse momentum theorem stuff. I think we have good examples of impulse. No, I'm going to add it. I'm going to add it in. So let's say if that tennis ball comes to a stop, to a stop, hitting
Kayla just texted me saying that her and her dad are having internet issues and to tell you guys.
All right, thanks, Paige.
Should we just chill out here or like leave for the day?
We should probably stay, Sarah. They're probably gonna come back.
I hope they don't.
I'm on WTC too, same as them, and it just went up for me too, but it just came back on, so they'll probably just got theirs too.
Okay, cool.
All right, am I back online? Can you hear me?
Yeah.
Great, sorry about that. My internet went down. I had to go, I followed the standard protocol for IT help, skipped the phone call. I knew they tell me to turn it all off, turn it all back on, and it worked. So here we go. Where were we? We were talking about,
A tennis ball.
I was going to add a new question. So if the tennis ball comes to a stop hitting muddy ground, let's compare. Case one, one would be if it's like very firm muddy ground, versus case two, where it's soft muddy ground.
You need to start the recording and share your screen.
Yeah, I just got to share the screen, but the recording I think is already still going because I didn't. Yeah, but I'll share the screen. Absolutely, thank you. So it looks like the recording is still going though. So even though I ducked out of the meeting because of internet problems and that, it stays going. All right, so case one, firm muddy ground versus case two, soft muddy ground. So we have, let's just use that original number of V1, being the 33, right? In fact, we can just use the number from here, which was the change in momentum was 1.89, right? So, yeah, that's right. Change in momentum from here was 1.89. So let's just say, recall, right? We know that's true, right? So we've got this value, 1.89, right? In both cases, the momentum is changing, right? So basically, the momentum reduces to 0, of course. So in other words, change of momentum is negative 8.9. 1.89. that is, kilograms meters per second. It's reducing, right? So in the firm muddy ground, the time interval might take 0.1 of a second or something like that, 0.01 of a second. In the soft muddy ground, the time interval might take almost a whole second, like 0.8 seconds or something. Okay. Question is, what kind of forces are exerted on the ball? So forces on the ball. During the slowdown, right? And we know that the change in momentum equals F delta T in both cases. So we can put in the minus 1.89. The negative is irrelevant really in this case here, of course, but we can talk about it as well. Same thing over here, delta P equals F delta T. And so minus 1.89. And we've got our 8.8 seconds. Oops. 8 seconds. What do I want to do here? Erase. F 0.8. I'm just going to get rid of this thing. There we go. Yeah, so that leads to answers of, this is going to be the same as multiplying by like 100. So I know this is 189 newtons. So this is minus 189 newtons. The direction system here would have been presumably that down was positive, and so you could tell that that's up based on that numerical analysis. So your answer in the end is therefore blah blah blah, right? Therefore the force on the ball was 189 newtons up, whereas the 1.89 divided by 0.8 becomes only 2.3625. Negative 2.3625 newtons. Right, and this is up, of course, as well, but you can see here a much smaller force. And that is your example in this lesson to do with the impulse and momentum theorem. Okay, the ball has a chance to slow down gradually by splatting in soft mud. Then the forces are less, whereas if it hits still firm, it's still muddy, it's still going to come to a stop, it's still going to stick, it's not going to bounce, right? But it's going to come together, or going to come to a stop much quicker. And so the forces will be much more. Any questions? All right. So that's an impulse momentum example to do with that tennis ball question, based on the original amount rather than the extended force option, right? But this was just more force for longer means more momentum change, right? So force acting for longer. So it's related for sure, but it's not the same idea as what we've been talking about. It's the main focus, right? So in marketing, same as the smart car thing, right? But some people get it and some people don't. So we've got Z-Shock crushes the competition. They're showing how rigid this yellow helmet is. Okay, they put a force on it in this hydraulic press, and it's not compressing very much in comparison to this crappy Bauer 9500, which collapses when you press on it. Okay, so that's their advertising there. This is amazing because it's so rigid, right? Versus the Messier project. Okay, Marc Messier developed a helmet that has technology in it where it can compress and absorb energy. So it can compress up to 80%. And if you read through it all, it says maximize compression, impact attenuation, lateral energy displacement, blah, blah, blah. Basically, maximize compression increases the time interval, which decreases the force that gets transferred to your noggin, right? John Tavares should have been wearing one of those. Hopefully he's okay, goodness sakes. But yeah, the better your helmet is at absorbing energy, the better. Now, the two things that are bad are that, well, okay, first of all, which one's thumbs up and which one's thumbs down? It's pretty obvious, right? That maybe I don't have to wait here. Clearly this one's thumbs down, the Z-Shock, and this one's thumbs up in the idea of absorbing energy, right? The other bad thing here, so first of all, this is bad, right? We don't want it to be rigid, right? Crush resistance, that's bad. Ridiculously light, that's also bad, right? Because ideally, if you had a heavier helmet, I know it's not as comfortable and whatever else, but that's going to essentially absorb, because that mass is inertia. It's essentially going to absorb a lot of that force. What it does, though, we say essentially absorbs a lot of the force, right? What it really does now is, if you look at it, is it the force that it gets acted on your head, it's not going to allow your head helmet system to accelerate as much, right? Because there's extra mass on the helmet itself. So your change in velocity ends up being less overall, which means the change in momentum of your head is less, which means the force on your head is less. So it's a bit of a step-by-step discussion to go through, but it's just crazy. I find it crazy to see this advertising, and it's just like how wrong they are in their science. And they probably, honestly, Easton probably knows it. They're going to have people working for them that understand high school level physics, right? But what sells, right? This product sells because it's light and flashy and it's tough, and if people just don't know better, they buy it. And we have an epidemic of concussions in ice hockey, as the Americans call it. Questions? All right, so 40 so momentum and collisions. So I start to make use of the fact that momentum's conserved. This was all more so about the idea of change in momentum. This was more about impulse. This lesson was the concept of momentum, and then it was, the idea of impulse and the change momentum. That's a big focus on that lesson. This lesson uses this stuff again. Remember this? Obviously it's just today, so momentum's conserved, right? So initial momentum equals final momentum. Another way you could say is delta P equals 0. All this means the same thing. Okay, momentum is conserved if there's no external inbound forces, right? Basically, if you're in a system where there's no external forces, or if you're counting the whole system in which forces are being applied. Oh yeah, this I'm pointing out here that this P with a little apostrophe, people call that P prime, and it means final momentum. So I automatically just see this as initial momentum, final momentum. Okay, it's a new bit of notation for us to make what we're going to be doing next easier on the writing utensil. Okay, so nothing new so far. That's just concentration momentum. We know it's conserved. So yeah, I'll show this one. I guess it's neat.
Conservation of momentum tells us that the total momentum in any closed system will remain the same all the time. And since momentum is equal to mass times velocity, even if you have multiple objects going at different speeds that might collide, for example, the total momentum of the system before and after the collision will remain constant. So for example, these two balls, which in this case happen to be of equal mass, whether one of them is moving, it causes the other to move, or they're both moving and collide and move off in different directions, the total speed and the total mass of the entire system always remains the same. So for example, if this...
So he said total speed and total mass always remains the same, and people usually just word it as the total momentum of the system remains the same. So right now this ball has no momentum. This one's going to come in with some momentum.
At a velocity of 0, and then at the velocity...
And then it goes. This one goes out with a bunch more of a momentum. This one ended up with whatever momentum it ended up with, right? But the total of the momentums ends up the same. So
the first one might impart some of its momentum onto the second, but the total between the two remains the same. And that remains the same whether one remains still and the other comes to collide with it, or whether they're colliding with each other.
So we're not going to be doing this next part today, but I just want to show it to you. So we put some Velcro on each.
In case I put Velcro. It even works if these two...
So even worse if they get stuck together, and that's going to be one of our analyzing momentum and collisions kind of cases that we're going to cover. Okay, so this idea of it
even works if these two stick together.
So the combined momentum of those two is equal to the momentum that they individually had added up. Okay, so they both had momentum, and then they end up with this combined momentum. So those are a preview of some of the things we're going to do. So we're going to analyze linear one-dimensional straight line, x direction only, however you want to word it, momentum, since it's easier. Obviously, this video gives you a good dose of reality that we really need to be able to understand momentum in 3D eventually, but certainly we're going to tackle 1 dimensions first, then 2 dimensions. I don't think we hit 3-dimensional conservation momentum in this course because it's just ugly to try and do. But the main idea is we are eventually going to be needing to focus on this, right? That the total momentum in each direction is conserved. So basically, in a 2-dimensional version, you'd be like momentum in the x direction initially equals the momentum in the x direction in the end, and we'd have momentum in the y direction initially equals the momentum in the y direction in the end, right? And so this will lead to numbers, right? Numbers, dot, 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 and answers, right? And then this will lead to a different set of numbers and answers. And you can't work with them both in the same equation and just pretend they work the same. Vectors matter, angles matter, right? So that's what we're leading towards eventually. So hopefully just easier stuff for now, just linear stuff, right? So this is just a picture about concepts, but picture mass 1 and mass 2 coming in with velocities 1 and 2, right? So the total momentum here would be like m1 v1 plus m2 v2. That's the total initial momentum, right? Notice that these are vectors, of course, so there's going to be pluses and minuses to do with forwards and backwards and so on. So this, for example, might go in as a positive number here if we chose this direction as positive, and then this would go in, right, the v there. This one would go in as minus number, right, to do with the angles and so on. Not angles, but directions, I should say. Okay, so this is m1 v1 plus m2 v2. We used in the past v1 and v2, meaning initial and final velocities, and I'm contemplating the next time I teach grade 11 not doing that at all, because I definitely, when I was first starting to do some of these in doing the solution sets and that, my brain kept thinking of initial and final velocities, but this isn't. This is the velocity 1 initially, and this is velocity 2 initially. Okay, so you got to switch gears and think of those as just velocity of object 1 and velocity of object 2. In the end, we might end up with them bouncing off each other, and so you might get a final velocity this way and a final velocity that way, a v1 prime this way and a v2 prime that way, whatever. And so your final momentum would be m1 v1 prime plus m2 v2 prime. Okay, and the prime means final, as we talked about already. So overall, we know that momentum's conserved, which means that the initial momentum and the final momentum are the same. And so this is the equation that we need to add to our equation sheet. I might wait until I have a nicer, like a typed version of it. But yeah, momentum's conserved, conservation of momentum, m1 v1 plus m2 v2, and so on. I'll get the equation sheet loading though, just so we have it ready once we get there. Equations, EBCDE. All right. So m1 v1 plus m2 v2 equals m1 v1 prime plus m2 v2 prime. It's fun to say. You can play around with a lab to do this if you wanted. So you picture the initial and final velocities with a bunch of different scenarios. We are looking at, wait for it here. We are looking at 1-dimensional. They don't even do the 3-dimensional in the applet, of course, because it's just ridiculous to try and show. So they're showing like what would happen if you had like hopefully almost no velocity there, and this one comes in with some velocity, and to make it less confusing, I'm going to stop the reflection so it doesn't reflect off the wall. But you can see like, oh, it comes in and hits, and they're doing what they're doing, right? If I made the masses be the same, or close to the same, it was close there. And again, let's reset. Oh, I guess that doesn't work. Reset that way. So 0 and whatever. Now picture velocity coming in, and you get that, right? So that you can play around with this to sort of see in virtual land at least the kinds of things that can happen. Notice that the one ball went out and the other one stayed where the collision happened, like what sort of almost happened in that video from outer space in normal forcelessness. Yep, I said it. Normal forcelessness. That's the word in my world. So momentum in one-dimensional collisions. Okay, so cars on a track, for example, you know, the red and blue carts on a track, they can only go forwards and backwards, so it's one-dimensional. We know that initial momentum equals final momentum, or we could say it's specifically if we wanted to focus on the fact that we're talking about directions specific. Technically, we're talking about an X version of this, right? So we could say M1 V1 X plus M2 V2 X plus, but we don't really need to include the X's. Just showing it on this slide so that later on when we look at the two-dimensional stuff, it might help you pay attention to it. Momentum is somewhere down here. So new slide and M1 V1 plus so conservation of momentum. Okay, and we'll probably add to this as we go and include the X and Y and so on later on, but for now, that's a new equation for us. 48, yeah. All right, so here's an example. All worked out, or actually first we're analyzing, is momentum even really conserved? And the physics tells us that it is, because if you're colliding, then you know you've got like force of this one on that one, so force of M1 on M2 on M1, and then an equal and opposite reaction force, right? They're the same because of the Newton's third law. An equal and opposite reaction force would automatically happen from M1 on M2. So since they are equal and opposite because of the third law, we can analyze out that we'd have a mass times acceleration in each case here. That's just the second law. And so we have a delta V over a delta T, and just multiply the times out because they're in both sides of the equation as a factor. So multiply both sides by time to get rid of it. And we end up with, this is going to be a fast and dirty development here, but delta V is delta V is final minus initial velocities in both cases. And that algebraically expands out, like term, move it around, rearrange it. It gives you exactly what we said. Okay, so really, conservation of momentum is true, absolutely, and it's very easy to prove. It's actually just based on Newton's third law and second law. Okay, so third and second law. So if someone ever doubts it, be like, it's based on only two of Newton's laws, so yeah, it's pretty easy to justify that it's true. Let me just full size that for a moment for you. You can see the big picture. Okay, so we know this is true, Newton's third law. Action force equals reaction force. We know force equals mass times acceleration. We know delta V equals final minus initial velocities. And it works out algebraically to be M1 V1 plus M2 V2 equals M1 V1 prime plus M2 V2 prime. So actually surprisingly easy to prove. Okay,
So
pretty good.
what is prime?
Prime, remember, means, what does prime mean? Do we remember this from me having taught it a second ago? Prime means the final velocities, right? It even says somewhere here or not. It said on the other pages, but yeah, the prime means final. It was on the other lesson, I guess, but anyways, back wherever it was. Where did I talk about it? Somewhere around here. Anyways, you need me to show you, or you trust me now?
Yeah, that's fine.
I know it happened. It's just trying to find where I said it. Anyways, silly for me to just keep searching there. Clarification has been made. We're good to go. All right. So looking at the kind of results, just like in this applet, right? If you're just playing with physics carts, it's nice to be able to do that. So unfortunately, you get to just see a video of it right now because of our circumstances, but basically a bunch of different possible options, right? So here's one. If we have equal masses, And I showed you the simulation of it already. So you can probably predict what's going to happen. So red cart coming in with whatever velocity, and what happens? Blue cart goes off with velocity, red cart stays put. It's like that, right? So that is, one of the possible options, right? So one possible option is coming in velocity of 10, has a velocity of 0, ends up with, 10 and 0, just switching. There's lots of possible combinations of this, depending on what the details are of the interaction. For example, we could have, oh, this is the numbers for the equal mass version. Okay, so we'll do that first. So the equal mass case, if we had some numbers to do with this, so if we have a red cart coming with, say, 3 meters per second, it could have done it for 10. And we had the blue cart had initial velocity of 0. The red cart's final velocity is 0. If we analyze out what that would make the final velocity be here, certainly we're expecting 3, right? Because of our observations, we see that that's basically what it looks like. And so we just analyze it out. We look at it and say, okay, well, momentum's conserved, of course. And so we know initial momentum equals final momentum. T's are for totals, which is your M1 V1 plus M2 V2 stuff all added up. So that becomes this. So you've got your 0.25 the mass times the 3, the velocity it had, 0.25 times the 0, the velocity it had, the velocity we see for sure in the end, the 0, because we saw the other, the cart end up with stopped after it collides, and the other cart went off with a velocity. We're wondering what that velocity is. You can see here that works out to be 3. So this mathematically confirms that in this video here, the red cart comes in with a velocity, the blue cart goes out with the same velocity since this one stayed still, or ended up stopping, I should say. Okay. There's more to come with this for sure. One way we can change this up is we can have different masses. The other way we could change it up is by having like some paper on the front here that crumples and absorbs energy. That's the big picture. Eventually, we're going to be able to tackle that. Okay. For now, this idea of the velocities sort of transferring completely to the other one, you can see it working nicely in the video and in the math. Okay. Trying to decide for this next slide if I'm going to show both of these or not. I think I will. The next slide is we're going to analyze both of these later on in a future lesson. But there's lots of different possible values. I came back and made a note here, and I realized, oh, I didn't actually teach this yet, so I can do it however I want. But basically, if this had a momentum of 10 coming in, and this had a momentum of -4, so it's like bounces off, right? So this is large mass colliding with a big mass, little mass colliding with a large mass, or vice versa, however you want to word it. It's all relative. So this is a little one coming in, colliding with a big one. What's going to happen? Well, it's going to bounce off. I think it's pretty obvious, right? So let's watch. There it is, bounces off. So there it's coming off with a negative velocity, ending up with a negative velocity. This one ends up with a smaller positive velocity, right? So coming in, red one's coming in hot with whatever velocity you can think of it as. Blue one goes out with a smaller velocity. There it goes. Red one bounces back with some velocity. One more time. Coming in hot, bounces off, right? So if those numbers led to this, if it was coming in with 10 and this one had -4, you can tell this would have to be like 14, wouldn't it? 14 and -4 combined to be 10, right? So basically we could say, oh, okay, so the mass is, this one is double the mass. The details are here that this is actually double the mass, okay, if that was the case. So we've got the 1 times the 10, the 2 times this 1 unit of mass, right? Twice the mass times 0, 1 times the initial velocity there, 2 times the initial velocity there, right? So if that number was -4, we pretty soon are going to be able to do a special kind of collision, right? We'll see another value that is conserved in collisions and so on. It allows us to actually calculate both of these and say what really happens. For now, we're saying that if this one ends up with a momentum, am I back?
Yeah, you're back.
But that was a shorter internet delay. I wonder if they're working on it or something else is going. It's not actually my unit needing restarting. All right, we're back. Let's keep going. So the numbers here work out where just M1V1 stuff, end up solving and you get 7. So this would have to be 7. Okay, so that was just, I showed the mass stuff there, 1 kilogram, 2 kilograms, and so on, if that's what the numbers were. Okay, so we're going to do lots of these examples. You're going to have lots of practice with those to calculate what the course, what the matching velocity would be. But again, if this was a -4, then whatever, then it would be a corresponding of 7. When we analyze this one further, we'll find out that this is a bit of a special case. It's certainly not what this video was. Okay, the video would have been more like this one. Okay, so if the velocity or momentum, ended up being -1 on the way back, because it was not much, right, on the way back, what would the corresponding momentum and velocities be for the other one? So let me let you try that one for just brief here. Just run the numbers for what the final velocity would be of the blue one. It's all color coded to make it easy to follow. If we had an initial velocity of 10 and this final velocity v1 prime equal to -1 meters per second, of course. And this one works out more the way closer to the way this really is. Can't really describe it fully right now because we haven't done all the things that I need, but it has to do with how much energy is absorbed. So technically this one actually absorbs some energy, whereas this probably doesn't absorb at all. But anyways, we'll get there. So of course you've probably already done this. Right, M1V1 plus M2V2 plus M1V1 prime. And then you just plug in a mass of 1 and a velocity of 10. I'll just make sure you're on the right track. Okay, so I'll pause a little bit more. Let's finish those lines. If you can. If you can't, I'll show you how shortly. So of course you have the 2 and the 0, right? Which means nothing basically in the end. So you're gonna have a 10 over here because 10 plus 0 is just 10. We'd have the original mass of the 1 times the final velocity, which we're gonna put in as a -1. And the mass of 2 with the unknown velocity we're trying to figure out. And again, we're gonna see soon that we can calculate both the final velocities for some cases, special cases. But this becomes this equation pretty easily. Adding 1 to both sides gives us 11. Divide both sides by 2 gives us a final velocity of 5.5. Okay, so that would mean this one went off with 5.5. This one bounced back with -1, and that's a possible result. Right. All right. All of this is going to come together eventually here, but we'll come back to a golf ball question as well. So question for now is, we're not fully answering this yet actually, but is it possible I remember being asked this by my dad at one point, is it possible physics-wise for a golf ball to fly off faster than the club head came in with? And like I said, we're not fully answering this here, but let's just say if the club head came in with 50 meters per second, for example, and then you measured and you found that it slowed down to 30, which I don't see why that wouldn't be possible, right? So the club head slows down to 30. The initial velocity of the ball was 0. What's the final velocity of the ball? So this is, again, just another example of you saying, hey, momentum's conserved, so I'm going to use this equation. So plug in numbers. You got a 0.2 goes in for the mass of the club head. When I'm doing this, let me recommend something for you to help keep them separate when you're looking at them. I've been finding it easier in the solutions that I'm doing to have it be like m1 equals the 0.2 kilograms, right? And then below it, like initial velocity, if you've got it, right? So initial velocity, that one's the 50. No, actually, wait, I better use the same numbering system. I had it labeled the other way around. Obviously, it doesn't matter, but let's stick with what we had here. So M1 was 0.045. V1, initial velocity of the ball was 0. V1 prime is what we're looking for. My computer is really adding extra stuff on me here. Don't know why. Get rid of those. Whatever. Stop it. And then the other thing we had was like M2. So I'm grouping all the M1 stuff and V1s all together. And then the M2 was the 0.2 and V2, the initial velocity was 50. And the final velocity, V2 prime, is the 30, right? And I just find it a little bit easier to sort of keep them sort of organized left and right like that when you're referring to the equation and filling things in. Because then you can say, oh, there's the mass and the velocity, boom, there it goes. And then, the other mass and the velocity, oh, there it goes together, lumping these things together. And so, anyways, the numbers go in consistent or correctly. And you just calculate what you get. That obviously goes to 0, so it goes away. This becomes these numbers. Take away 6 from both sides. Gives us a 4. Dividing both sides gave us a final velocity of, if the club had slowed down to 30, it would give us a final velocity of 88.9 meters per second. So the club head came in at 50, and depending on how much it slows down, if it slowed down to 30, it would give you a crazy velocity of 88.9 meters per second. Like multiplied by 3.6, that's crazy fast. Okay, so at least in terms of momentum, right? Momentum can be conserved, right? So momentum can be conserved even if the velocity of the ball, ends up faster than the club head. So it's possible. Doesn't necessarily say we've concluded that it does happen, right? But at least it's possible in terms of conservation of momentum, right? So it's possible in terms of delta P equals 0. It happening wouldn't violate the law of conservation of momentum, right? It wouldn't violate the law, right? So it's possible. Okay. Questions?
Yeah, I'm not really sure like how getting the 88, like how getting that answer proved it. I'm not sure what we were looking for.
It didn't prove it. What it did, all it did for now, because we need another concept. We need what's called elastic collisions and the idea of other things involved with this. We need energy concepts at the same time in order to really determine it. But what I did determine here is that if the club head changed by this velocity, then it would lead to this velocity as a result of momentum being conserved, basically. So if someone asked the question, Sarah, this way, would it violate the law of conservation of momentum for a ball to go off faster than the club hit it with? Right? The answer to the question, phrased that way, is answered fully here. Be like, no, it wouldn't violate the law of conservation of momentum. You definitely could have a velocity of like 89, even though the club only came in with 50. Okay, it wouldn't violate the law of conservation of momentum. Does that help you?
Yes, it does. Thanks.
Perfect. Yeah. So I'm not fully confirming that this happens in real life, just to be clear, right? So this doesn't prove that it happens in real life. IRL. Just that it might, since it doesn't, since it doesn't violate. There we go. So that, yeah, right there. Now I'm dividing, just like in the uniform acceleration stuff, I divided into like type 1, 2, 3, 4, 5, all the way up to like 8 or whatever. These ones I've divided into, I think, 4 types. So I'm not committed to only showing, what do we got there? 48, 49. Let's see if maybe start looking at type 2 at least, because it's really the same stuff, and we still have 45 minutes of class time left. Technically, it's only 15 of virtual, but so I don't want to fall behind, and I don't want to not show you stuff, because I don't want you to fall behind. Knowledge, at least. So let's see what we got here. So looking at type 2 is when energy is released, and type 3 is when you have like a velocity, like you're walking on a raft. If you get up in a canoe and you walk, the canoe kicks backwards and you kick forward, so analyzing momentum in those situations. So there's lots of different types of situations for us to tackle. So let's see what we can feel good about here and get done. So a question that could stump you later if you don't consider it. Wow, it's not really that fundamental, to be honest, but if momentum's always conserved, how can any object at rest end up moving? And obviously it has to do with the idea of whole system versus like components of a system, right? So, if you're talking about the whole system, then momentum is conserved, but that doesn't mean that object A can't like spring off of object B and they end up flying away from each other, total momentum still being 0, right? So recall, we're talking about a change in momentum comes from a force times a time and so on. But this is for individual parts of a system, whereas the whole system overall, of course, would still have change momentum as 0. And there's definitely a question written out from the homework in good detail there for you to see more clarification about that if needed, right? But the whole system, like 2 masses colliding, for example, all of the momentum before and after, all the bits added up would be the same before and after, right? If you're talking about, so that's just the regular stuff, right? The only time it's a little bit weird is if you have like action at a distance, especially like gravity and magnetic repulsions and so on. It can seem like something, end up getting momentum. But you have to consider the momentum on the other object as well. So the big one that's weird, this is going to do a little bit better job of what I've already talked about in the beginning of the lesson. Remember I said I'm going to erase it because it just maybe isn't the best. We didn't fully cover it yet, let's put it that way. So the most common example in which it seems like momentum is not conserved is when one mass is very large, particularly if you're considering a mass that you're accelerating or whatever, and then the other mass, if the other mass is the Earth, right? So for example, if you started walking and ended up changing your momentum from 0 to some positive value, it might seem like momentum has not been conserved. However, if you include the Earth in the analysis, momentum is conserved. Because it's a law, right? It has to be conserved. The velocity of the Earth in the opposite direction, right? The velocity that Earth gets in the opposite direction actually balances out that momentum you got in the other direction. So it has a matching negative momentum, which is obviously not very noticeable due to its very large mass. And I hope the obviousness works out in the equations here. Okay. So to start with, no momentum at all, no velocity either way. Okay, you and the Earth both at rest relative to each other. Okay. Yeah. So you with your zero momentum, Earth with its zero momentum. So you end up deciding, oh, I'm going to walk forwards. I'm going to have a positive momentum. And then the Earth supposedly gets, and I say supposedly gets because it's probably hard to believe, right? But it really does have a negative momentum the other way. But the issue is that your velocity is noticeable, whereas the Earth's velocity is not noticeable. Okay. And so if you work the numbers out here, there's an example on the next page, but basically same value, just opposite directions, right? So basically 0 equals 0 still. So a number value to do with this is worked out somewhere. I just losing, maybe it's in the homework. But let's just do numbers here to show it. So basically, if you had a mass of say 50 kilograms, and you ended up going like, I don't know, let's say you end up going a really fast speed, like even if you went like a 100 meters per second, that's 360 kilometers per hour. What velocity would the Earth have to balance that? Remember, 5.98 times 10 to the 24, right? So what velocity would the Earth have to have? This is v2 prime of the Earth. What would it have to balance your crazy 360 kilometer per hour velocity, right? Surely it must be noticeable if you're going that fast, right? Well, turns out not so much because of this giant number. So we have here 5,000 plus the 5.98 times 10 to the 24, v2 prime. Just taking away from both sides gives us a minus 5,000. But what do we get when we divide 5,000, which is lots of momentum, but we divide it by 5.98 10 to the 24? Well, 5,000 divided by 5.98 10 to the 24 gives me 8.36 times 10 to the negative 22. Okay, this is the velocity the Earth would have. Right, this is the velocity the Earth has, but it's of course not noticeable. Well, I'm supposed to say noticeable. Okay, it's an extremely small number because of this. Okay. Questions? Kind of weird to think of, but if you jump up, you're pushing on the Earth. The resulting reaction force is the force of the Earth up on you, making you go up. Your force on the Earth obviously pushed the Earth the other way, right? So technically you both move out and then come back together, right? But you go up a heck of a lot more than the Earth goes the other way. Like you go up a noticeable amount, the Earth goes down a not noticeable amount. Is there a question there?
Yeah, I was gonna ask, I don't know if this makes sense at all, but would that mean like the Earth wouldn't really spin with like a constant velocity? Like since that's just like one person, right? If everybody on Earth's doing something, wouldn't that all kind of affect the Earth?
So if you're thinking that, the question is what if everyone, we did this in grade 11 a little bit, but what if everyone on Earth jumped at once, right? And so if I look up what if, it's supposed to be on the actual what if website. Basically what happens is even if everybody was on one side of the Earth at the same spot and everybody jumped at the same time and so on, the end result is basically nothing happens at all. But there's an analysis in the grade 11 lessons, just looking for the actual website. Maybe, I think it was called What If. Let me go back one step here. And I'm just going to clone that page there. I'm going to look up What If website. Something like that. Ooh, that's close. So What If. website. I don't know where it is anymore. I can't find it right now. What ifs? How? I don't think that's it. I'll have to. What I'll do is I can find the grade 11 version of it. What if humans didn't have males? Ugh. This might be the one. I don't think so. It doesn't look like it, but what if every jump at once? The end result of the physics analysis is pretty quick. It'd be like, basically you wouldn't notice it at all. Same in a plane, you wouldn't notice it at all because the plane's so heavy, right? And then the what if website, I probably won't actually bother going to find it because it's a null result. Basically, it's the Earth, you wouldn't notice it. It would move so little, right? This looks like it, actually. Is it a video or is it a picture? What's going on here? It is a video. Interesting.
The back end of your site is like an endless, intricate system of water pipes. When there's a leak leading to a flood,
so they're gonna end up talking about the complications of having everybody all in the same spot at once.
At the same time, all 7 billion of us would definitely make an impact. But it's not the one you might think. First, let's gather everyone into one spot.
Yeah, this
that
is
way
the
we all know exactly when
the video version of the analysis from the grade 11 class.
3, 2, 1, jump.
Everybody jumps up
If all
and
7
then
billion
down.
people jump 1 foot in the air, we land at the same time. At that same instant, we release an enormous amount of energy. Some of the energy will be absorbed by our shoes, while the rest will mostly go into the air and ground. One of the first things we notice is a tremendous sound like thunderous applause. The volume would reach around 200 decibels, which is loud enough to shatter eardrums. At the same time, we start to feel the ground begin to shake. The vibrations from landing would cause anywhere from a magnitude 4 to
That's pretty cool.
The size depends on how much energy the ground absorbs compared to our shoes. While a magnitude 4 earthquake wouldn't cause much damage, a magnitude 8.
I think they're talking about if we manage to squeeze people into like a really small area.
Collapse electrical lines. Then train rails out of shape.
I don't know about that. That's if you had everybody manage to squeeze into a very small area. So the version from the grade 11 class is better because it's more realistic. That you're not going to make a tsunami. Like people would be spread out so far because obviously it just people can't fit all in one spot. So that spreads out the force, making you not cause an earthquake and making you not cause a tsunami and so on. But the rest of the analysis in the grade 11 one still, you really talk about just the complication of getting home after that. It'd be like, obviously, gridlock on the highways, cell phone communications would go down because there'd be so many people trying to call someone, like and just chaos ensues afterwards. So it's a silly analysis, but the main result is this, that you wouldn't notice anything. The Earth is just so massive, we wouldn't notice anything. Does that answer your question?
Yeah, it does. Thanks.
Yeah, no worries. All right, so the lesson 48 we tackled. 47 too, I guess. Is that what it was? Or the numbers here? Yeah, 47. So I will show you those. Just take a quick screenshot of it if you want to make it easier for you to keep track of what's there. These ones, if I remember right, are the ones that are just like idea based, and then these are like straight calculations, like plug in M and V, get momentum. Like these are going to be pretty quick and easy. You just have to do them and get to know them and be good at them. And then some of these are going to be like the M1 V1, M2 V2 stuff. Okay. So I'll screenshot of that. I'll be posting all this shortly anyways, but if it's easier for you. And then we tackled the first part of this one. So I'm going to post the solutions for that part. Just don't worry about the rest of the solutions for the other stuff. We'll get to that tomorrow. All right. Yeah. A little bit nervous that there'd be something in here that we didn't cover yet, but the solutions are going to be posted as well, so you can help yourself through that. But I think based on the way this is organized, it should be safe. Yeah, hopefully. All right. So don't worry about the rest of this lesson and all that, but I'll post it as is and then update it afterwards after we go through the rest of it tomorrow. So that is it for now for me. I'll be back on again at 1, of course, as always, or most always, when I can, to help out. Sorry about the internet delays, but things seem to be working again. That's good. Let me stop the recording. Hopefully it recorded fine. I think it did.